First, let us begin with Maxwell's equations. You have probably already studied them in electromagnetics. Maxwell's equations consist of these four equations. The symbols have the following meanings. E is the electric field. D is the electric flux density or electric displacement. B is the magnetic flux density or magnetic induction. H is the magnetic field or magnetic intensity. J is the current density and ρ is the charge density. All of these quantities are functions of position r and time t. Such quantities are called fields. In other words, fields are physical quantities defined at every point in space. The relations among these fields are summarized by Maxwell's equations. Equation 1 is called Faraday's induction law. Nabla cross E, which means the curl of E is equal to minus the time derivative of B. Equation 2 is Gauss's law. The divergence of D is equal to the charge density. The third equation has the same structure as the first equation. The curl of H is equal to the time derivative of D plus the current density J. The fourth equation says that the divergence of B is always zero. In other words, the magnetic flux density B has no sources or sinks, meaning that no magnetic charge exists. Now let us briefly recall what these operators mean. The curl operator acts on a vector field, and the result is again a vector field. Its magnitude represents how strongly the field rotates around that point, and its direction is given by the right-hand rule. The quantity nabla.d is the divergence of D. This gives a scalar field. It tells us how strongly the vector field D is diverging from each point. If the field converges instead, the value becomes negative. Next, let us examine whether Maxwell's equations can determine electromagnetic fields by counting the number of unknowns and equations. If the source terms J and ρ are given, we would like to determine E, D, B, and H. These are four vector fields. Each vector field has three components, so the number of unknown scalar quantities is 12. On the other hand, Maxwell's equations provide only 8 scalar equations. Equations 1 and 3 are vector equations, so together they give 6 scalar relations. Equations 2 and 4 are scalar equations, so in total we have 8. Therefore, Maxwell's equations alone are not sufficient. We need additional relations called constitutive equations. For example, D equals epsilon E and B equals mu h. These are vector equations, so together they provide 6 more scalar relations. In a conducting medium, we also use Ohm's law. J sub C equals sigma E for the conduction current. This relation is also included as a constitutive equation. At first sight, it may seem that we now have too many equations because now we seem to have 8 plus 6, that is 14 equations. However, 2 of the divergence equations act as constraints, or initial conditions, rather than independent equations. For example, if we take the divergence of equation 1, we obtain the divergence of the curl of E. But it is a fundamental identity of vector calculus that the divergence of a curl is always 0. Therefore, we obtain the time derivative of the divergence of B equals 0. This means that the divergence of B is a constant in time. So, this equation represents an initial condition that says the constant C is 0. After taking these constraints into account, we have 14 minus 2. That is 12 equations, the right number of independent equations. Now, to make Maxwell's equations easier to handle, we take the Fourier transform with respect to time. For example, we define E of r and angular frequency omega as the Fourier transform of E of r and t. Then each field becomes a function of position r and omega. If we take Fourier transform of the curl of E, we can interchange spatial differentiation and time integration because they are independent operations. So the result is simply the curl of E of r and omega. For the time derivative term, we apply integration by parts. Assuming that the field vanishes as t goes to plus or minus infinity, the boundary term becomes 0. The remaining term gives j omega times. This integration is identical to the Fourier transform of b, so the result is j omega times b of r and omega. Applying the same procedure to all 4 equations, Maxwell's equations become this frequency domain form. The important point is that a time derivative is replaced by simple multiplication by j omega. This is one of the major advantages of the Fourier transform. It converts differential equations in time into algebraic relations in frequency. From now on, we will use these equations to study how electromagnetic fields are generated by given current density and charge density.